Okay, we are back and we are going to look briefly at standard deviation. And so whenever we have a data set and we're talking about its distribution or how spread out that data set is, we want to be able to quantify it, not only so that we can talk about data points within that set and how close they are to the mean, where they are along the distribution, but also comparing different data sets and how spread out or tightly clustered they might be. Right. So this idea that we're going to talk about is what we call standard deviation, which many of you have probably heard of or dealt with. So just a few points of notation. X bar is going to be our arithmetic mean. In other words, taking all the data points, adding them together, and then dividing by how many data points we have. So x sub I, or x sub 1, x sub 2, all the way up to x sub n, would be those respective data points. So in this case, we might have a mean of 5 foot 2.5 inches, 5 foot 2.5 inches, and each of these xi's would really be just one of the measurements that a student took. So there would be 100 different data points. All right, so our goal is to associate a number to the intuitive idea that some data sets are spread out widely and some are more tightly clustered. And we're going to do it via standard deviation. So the first thing we might want to do, or a good instinct is to say, well, let's measure how far apart all of the data points are from the mean. If they're very close to the mean, if they're all very close to the mean, then it'll be a tightly bunched group. If they're spread out from the mean, it won't be as tightly bunched. Okay? So the problem with just doing that is if we've got a data point that's 1/10 higher, right, and a data point that's 1/10 lower, if we just add positive 1/10 plus negative 1/10, we get 0, right? So those things sort of undo each other. Right? So what we do instead, and there's many reasons why we go this route, but we take the sum of the squared distances from the mean. So each x sub I is again a data point, and so we find its distance from the mean by just doing x sub I minus x bar. Once we've got that distance, we take that whole quantity and we square it. So now all of these distances have been squared, so they're all positive. Right? All these new values are positive. We take them and we add them all up. Okay? So in some way we're summing the squared distances from the mean. It's exactly what we're doing. Then once we do that, we take what's called the square root mean. In other words, we have this sum up here. We divide it by however many data points we have. If you're unfamiliar with the sigma notation right here, all right, that means that we're adding between terms. We start with a counter I at 1, and we add the first term, and then make I equal to 2, and then add the second term, and continue on. But so when we take, anyway, sidetrack. When we take the square root mean, what we do is we take our sum of the squared distances from our mean, and we divide it by the number of data points we have. Once we do that, we take the square root of it. Okay? This value is the standard deviation of our data. Right. For those of you who've had statistics, this is the global standard deviation. We will talk about a sample standard deviation later, possibly. All right, but this gives us some measurement in telling us how spread out or tightly clustered our data is. And the bigger the standard deviation is, all right, the further spread out the data is. The smaller it is, the more tightly clustered it is. All right, so for example, in our example here, the standard deviation happened to be 2/10. One of the reasons we care about standard deviations so much is that with normal distributions, and it is by design important for normal distributions, all right, the standard deviation can tell us a lot about our data and where it falls. So in the case of normal distributions, fitting normal or bell curves, right, about 68% of our data differs from the mean by 1 standard deviation or less. Okay? In other words, it's within adding 1 standard deviation or subtracting 1 standard deviation. So let's see a picture. Let's look at what this looks like as a picture. So if this is our mean, right, whatever this value was is our mean, then subtracting off 1 standard deviation, the interval from there to adding on 1 standard deviation to the mean, about 68% of our data should fall within that range. So 68% of our data points, that frequency, should fall within, all right, that interval around our mean if we have a normal curve. Well, not only do we have that, we also have, all right, Well, what about 90 or within 2 standard deviations or less, obviously, of our mean? We should get about 95% of our data points, all right, within 2 standard deviations of our mean. And then about 99.7% of our data would differ from the mean by 3 standard deviations or less. All right. So if we've got a data point that's way out, so that's 3.5 standard deviations away from our mean, it's way outside the norm. All right. It's very unusual. Okay. So for example, let's look instead this time at the heights of Belmont students. And let's say the mean was 5'7" and the standard deviation was 3 inches. Okay. So if we have a normal distribution, what can we say about the data spread relative to the mean? Well, we should think that approximately 68% of the data lies within 1 standard deviation from our mean, 5'7". That means about 68% of our data should lie between 5'4" and 5'10". And we could go on like that, likewise. Right? So these percentages up here are valid for normal distributions, regardless of whether the distribution is has a small standard deviation or a large one. All right? And I even encourage you to take a moment and draw normal curves, one with a large standard deviation, one with a small one. All right. Our bridge from here to this next example is that measuring how far a data point is away from the mean makes most sense to do in terms of standard deviations. Right. In other words, that way we can compare it to data sets outside of or data points outside of its data set. In other words, how unusual is it compared to a different data point in a different data set? So the number of standard deviations that a data point is away from X bar, from the mean, is called its z-score. All right, its z-score. Okay, so typically if we're talking about just the difference between numbers, we measure the number of 1 units, right, away from something that is, right? So, in other words, 7 minus 4, 7 is 3 single units, right? 3 units away from 4, right? Well, if our standard deviation is 1.5, then 7 is 2 1.5s away from 4. In other words, it's 2 standard deviations away. Okay? That's what we're getting at with the z-score. And so let's go through this example. This next example, we'll briefly go through it. So I look at, in 1920, I've got the batting averages, the mean batting averages in the major leagues was 0.265, all right? And the standard deviation was 0.050, all right? Or 50 thousandths or 5 hundredths, however you want to say it, okay? And the data fit a normal distribution, okay? So what we could infer from this is within 1 standard deviation of our mean, all right, so we should see about 68% of the data. 68% of the players should have batting averages within 1 standard deviation of the mean. So that about 68% of those batting averages should lie between, well, 0.251 and 0.315, right? 50, or pardon me, 1 standard deviation above and below the mean. In the year 2000, the batting average mean was very similar, all right, but had a smaller standard deviation. So the data was, right, more tightly clustered than in 1920. And the data also fit a normal distribution. Again, what could we infer? We could infer something about, right, our data, given that we know it's a normal curve and we know the standard deviation and mean. Okay? Well, here's my task for you. All right. So, and this is why the z-score is so useful and important. So, Shoeless Joe Jackson batted 382 in 1920. Okay. And Moises Alou, that says Allo, it should say Moises Alou had a batting average of 355 in 2000. So we might want to know what are some ways we could compare these two players from very different eras. Well, a natural choice is the distance from the mean, right? But again, right, these two players lived in eras where they had different standard deviations. Okay, so the one player's distance from the mean doesn't translate to a player's distance from the mean in 1920 in just raw subtraction, raw difference. Doesn't translate quite well to the year 2000 in terms of a player's distance from the mean there. Okay, so what we do instead is we look at the number of standard deviations away from the mean each of these players is. It's their z-score. This is what we call their z-score. So here are the two histograms for each of these years, 1920 and 2000. All right, if you notice again, like we should expect given our standard deviation, in 2000, all right, the averages were more tightly clustered around our mean. There was a smaller standard deviation. All right, and so here's where Shoeless Joe fell in 1920, and here's where Moises Alou fell in 2000. So we want to measure how unusual, right, their batting averages were relative to their peers, relative to their data set, and compare them. Well, the z-score is our tool for that. The number of sigmas, the number of standard deviations that a datum is from the mean, is called its z-score, which is computed by, we take the difference from the mean and see how many standard deviations that is, right? In other words, we find the difference and divide it by what our standard deviation is for that year. Okay, so my challenge to you is to figure out the the z-scores for both Shoeless Joe in 1920 and Moises Alou in 2000. There's a reason why we chose these two players, right? So if you want, for example, you can also think about this in terms of this z-score in terms of the data point x is equal to sigma times z. So sigma standard deviation scaled by its z factor, z-score, pardon me, plus the mean. So if I want to get to my data point, I've got to start with the mean of my data set and add on so many z sigmas. Right? That's what the z-score is. All right, from here, there are some few questions that I just want to encourage you to look at because they're questions that are very good assessment type questions, just making sure you really understand the concept. I might come back and ask very similar things later on. But so a problem or two. I'm going to give you just some tips about it. So the average high in Anchorage in January is 21 degrees Fahrenheit with a standard deviation of 10 degrees. The average high in Honolulu is 80 degrees Fahrenheit with standard deviation of 8 degrees. So in which location would it be more unusual to have a day in January with a high of 57 degrees? So more unusual, right, is in some sense we're testing the likelihood of a January day with a high of 57. For Anchorage, it would be a great deal above the mean, and for Honolulu, it would be a great deal below. But what we want to do is we want to compare that data point to, all right, Honolulu's mean in terms of its standard deviation, and likewise with Anchorage in terms of its standard deviation. Okay, so what we're looking for is the z-score of both of this data point in both of these different data sets, right? So what's the z-score of 57 degrees in Anchorage, and what's the z-score of 57 degrees in Honolulu? And which one's more unusual? In other words, which one's more standard deviations away from the mean? Right? Less likely to occur. So for number 2, it says a classmate describes a study in which from her poli-sci class about a number of years a typical American works before retiring. So that's important. The number of years the typical American works before retiring. So not age of retirement, but number of years the typical American works. She remembers the mean value and the distribution. She knows the mean value, and she knew that the distribution was normal, but couldn't remember what the standard deviation was. And so here are your 3 options. So which one must it be and why? Only one of these makes sense, all right, given what we know about normal distributions and standard deviations. Okay, so only one of these values makes sense, and I would think about it in terms of how much of our data, how much of the population would have to work a certain number of years, given each of those different standard deviations. All right. The 3 questions that follow are all just, can you think through and justify what might be a normal distribution, a uniform, a bimodal, skewed distribution, that sort of thing. Just trying to test your intuition and working through. So from here, we're going to do a brief thing on statistical significance in the next video, and then we'll move on to correlation.